speaker, Dr. Dilum Bandara, who is an outstanding alumnus of University of Moratuwa. He is a senior research scientist and an expert on distributed systems such as blockchain, cloud, and P2P. And also, he has provided a great service as a lecturer in the computer science and engineering field for 16 years. I also warmly welcome Dr. Sulochana Suryarachi, who is joining with us today. And I like to warmly welcome all of you on behalf of ACM Student Chapter of the University of Moratuwa to the session 2 of Blockchain webinar series on blockchain platform design. So shall we continue?
Yeah. Could you allow me to share slides?
Okay, sir.
Okay, I can share. Hope you can see my screen.
Yes, sir.
Okay. How does this work? Usually you keep the video open, or probably to say a little bit of bandwidth maybe for students, if I can switch it off if that works as well. What would you recommend?
Yes, sir. We are recording right now, and there are 4 co-hosts right now, sir.
Okay, so let me stop video for the moment. Okay, so I think there's a slide thing I need to mention. The title is little, oh, I opened the wrong slide. Let me, yeah. I think this is consistent with the advertised title, which is on blockchain platforms. But I don't want to talk so much about the technical aspects. So what I understand is Dr. Srinath last time kind of gave you a pretty good overview about the whole idea of blockchain, what they are not, kind of a thing. And what I would kind of like to do today is to kind of go more into details, or let's say the more technical stuff into that. But on the other hand, I don't want to make this like a lecture. This is actually extracted from 2 lectures that I run here. But this is like this slide set which I will share. It's more like to complete the story I'm going to go through today, but not necessarily I'm planning to go through every slide. So if we start with very quick review of what a blockchain is, the whole idea, or let's say the whole goal of blockchain is to replace this middleman between 2 transacting parties. So let's say if 2 organizations are involved in some sort of a business relationship, so in things like Bitcoin, it's about, let's say, payments. And you usually have this middleman, like let's say if you and this is your friend, you have a bank in the middle. So the idea of blockchain is to essentially replace this middleman with a set of computers formed into a network, a peer-to-peer network. So we replace this traditional trusted environment with a blockchain trustless environment. Now, so what I mean by trustless here is none of these individual nodes itself are trustable. But as a collective, we can trust them because each other can check and validate what the other node did, whether it makes sense or not, or whether it's valid or not. So as a collective, it is trustable, but not necessarily we really believe, or let's say we trust any of these individual nodes. So it's a decentralized network that are formed in a certain way. So what I'm really going to talk about is how this is really formed today, and some of the things around that. Now, then the whole idea, so how you get this trustless environment is through this idea of a blockchain. This is not the only way to do it, but this seems to be one of the most comprehensive, one of the most acceptable ways of doing this. So you have a set of transactions, you collect a set of transactions and form something called a block, and this block is always linked to the previous block. And this block is linked to the previous block like that. And the very first block, we call that the Genesis block. So certain technical things are happening in this phase in terms of hashing, digital signatures, and things like that, which kind of makes it difficult. So let's say if I change a transaction here, the signature, or let's say the fingerprint of this block is going to change. Because of that, it'll have an impact on this block. So that's fingerprint will also change because it's always point to the previous block. So it's essentially what is called a replicated and a distributed ledger. In simple, let's say, data structures and algorithms point of view, we could look at this like a massive data linked list. But there are a couple of technologies behind this, things like cryptography and hashing, which I'll kind of go through a single slide introduction around this. But before going into any of these technical details, let me take you to a website called ETHweaver, which is developed by our team, which I currently maintain. Hope everyone can see my screen. Let me make this a little bit bigger. So this is a live visualization of the Ethereum network. This is what is currently happening. So this is like the most recent block. And this actually got generated about a minute ago. Sometimes this visualization can be even ahead. Sometimes it can be a little bit behind. It can be usually a few seconds to a minute or two in most cases. Yeah. Okay, so if you like look at this one, so this like the Etherscan is like a web browser, or let's say search engine, not a browser, for things happening in the Ethereum network. So these are set up blocks. And what we see is some of the transactions that are pending to be included in one of these blocks. So here we are only visualizing above 500, but as far as we know, there are 10,000 transactions, but some other nodes actually may know a lot more than this. So some of these transactions will go into the next blocks once that get generated. So let's say this block is 14 million something. We just go with the last two digits, let's say 75. The one before that is 74. So 75 links to 74, 74 links to 73, like that. And what we are seeing is this particular block has quite a lot of transactions. Maybe, yeah, compared to this block, and this one has much less. Now, what we just see here, this red one is interesting. Now, if you look at, there are two blocks with the same ID, not the ID, this is actually the block number, let's say 975 and 975. And whereas this 976, the one that got generated later, it decides to take this block as its parent block, not this one. But whereas it's still recognized, there is another competing block for 975, and it has this scattered line here, what we call an uncle block. So it recognizes that there is this block, but it decides, I'm not going to be concerned about this block, but I'm going to be concerned about this one. Now, this 975 is also an interesting block, because if you really look at that, and let's see, where can we see the number of transaction again? So I better make this bigger. I'll talk about some of these things, but if you look at this one, there are no transaction in this block. So there is essentially 0 transactions. Whereas let's say a block like this one, we have 427 transactions. So then 4696 get generated, and then someone will use that one and then generate 49977. So some of those transactions went to this one, and there were a lot of other transactions that are not shown here that also went into this one. So this is pretty much what happens in the blockchain space. You collect a set of transactions, form a block, and then you link that to the previous block, and then you move on. So you start building the next transaction from these pending set of transactions. Now, here there are a few other things as well. Like, let's say if you look at this big circle here, if I click this one, should be able to click. Oh, it went, oh, disappears. It went into this block, but maybe something like this one. So here's a pending transaction that was issued to the network of almost a minute ago, and from a certain address to a certain address. I'll talk about what each of these means. And so why we have this one is essentially what is called a smart contract. So that is why we have this icon. Let me go back here to indicate the smart contracts, whereas other ones, so if you look at some of these, you have the ether value, the value of that transaction. So this one, no value, but it may be executing a smart contract, whereas some of the other circles like this one, so that has 10 ether. So if you look at like in Australian dollars, or let's say American dollars, so this is probably like 20,000 US dollars in this transaction. So like that, the network continue to go, and typically a block gets generated every, let's say, 13 to 15 seconds. Sometimes you would see it happens much faster. Sometimes you would see it happens much slower, but the average number is around 13 seconds to 15 seconds. Okay, so if I leave this and then start talking about one of these transactions in detail, hopefully this will continue to run and we may be able to see some more interesting things as we go on. Okay, so this one is still pending. Let me take a transaction that got included in a block. So let's talk about, yeah, okay, so this block, this is block number 972, and that got generated about 3 minutes ago. Time is in UTC. And this particular block has 427 transactions and something called internal transactions. So internal transaction is like, let's say within your class, you may have a function and that function may call another function in the class like that. So that's essentially what is happening here. You could probably ignore that at this point. And then MindBuy is who generated this one. So if you actually go to, maybe I'll even force this on the chat. Oh, where is the chat? So there is someone that built this block, and who that someone we could assume based on this address, a miner called ETHMine. And it took the miner 5 seconds to generate this block. And because the miner generated this block, miner also gets a certain reward. So it got 2 point something. So $2 were not $2, 2 ether were given as the reward. Plus the miner was able to collect some money in as transaction fees. And there's no uncle here, and there's something called difficulty, which we will talk about later. And the size of the block is fairly small, only 144 kilobytes about. And this use what is called gas. I'll talk about that as we go on. And so these two are related. And what else? So this block has a unique hash. So this is what we call the unique ID of the block, because there can be, like, if you remember, like there can be 2 blocks with the same ID, like 975, 975, but each of them will have a different hash. So that is how you really identify one block from another. And the parent hash, the block before, so this is 972. We can try to go to 971. Yep, and if you just notice the hash, let's say current hash is something like 5Z, starting with 5Z and ending with 404. So if you really look at this one, the parent hash is that one, 5Z 404. And if you have uncles, you will also have some additional things, and there is this thing called nonce, which I will talk about later as well. So this block has this 427 transactions. If we talk about one of those transactions, so let's say we just take one of these, maybe we'll just take a simple one. Yeah, maybe something like this one first. So we have a transaction. So transaction also has a unique ID, which is the transaction hash. And whether this transaction is successful or not, sometimes when there are things like exceptions, the transaction may fail. And when this transaction occurred, it's essentially the same as the block time. And who is the sender of this transaction? Who is the receiver of this one? So essentially, if you are paying someone, who is paying and who is receiving that money? So we identify all of these as this hexadecimal string. And what is the value of this transaction? It's pretty small, effective to 5.63 US dollars. And as for this transaction, the party that initiated the transaction has paid 87 cents as the transaction fee. Again, let me skip about gas for the moment. And there are few other additional things. So this is what is called a typical transaction. Whereas let's call something like, let's say maybe something like withdraw. This should ideally be hitting a smart contract, which is essentially a piece of code that is deployed on a blockchain. So again, you have a signature, transaction is successful, which block, at what time. And this is related to a smart contract called Uniswap, which essentially can swap tokens. So let's say you can give Ether and get Bitcoin, or give Bitcoin and get something else like that. And then again, who is the initiator and the target, who is the receiver of this, in this case, not an individual, but this is what is called a smart contract. In this case, you didn't really transfer any money directly as Ether, but you still paid a transaction fee, $1.26. And there are a few additional things, but this is something more important. We didn't see this one in the previous case because it was just a money transaction, whereas here you're actually invoking a function in the Uniswap smart contract, and the name of the function is withdrawal. And to the function, your input is how much you are going to withdraw amount. And so your amount is actually given as this. We can actually see this. So this is essentially when you convert this whole thing into hexadecimal string, that essentially says, okay, it was this particular function, and this was the value that was sent into that function. You could actually decode this one, and this is actually what you try to withdraw from that. It looks like a pretty big number, but not necessarily, because you may have like 10 fraction points. Or even maybe more even, like let's say 12 or 18 like that. So in that case, it can actually be a fairly small amount as well. Now, if I now go into a little bit about this smart contract, let's kick this one. So it's a smart contract that has quite a lot of Ether. So this is 5 million Ether. Just so multiply this at least by, let's say, 2,000 American dollars. And so this is holding quite a lot of money. Okay, so it's actually here. It's about what, 10 billion US, almost 10 billion US dollars. And there are quite a lot of transactions that are happening here. So under this particular smart contract, or let's say this particular address, there has been more than 8 million transactions. So this is one of the most active smart contracts in the Ethereum network. But the more important thing is, if you go and click on this contract, you can actually see the source code. Some people put only the function signatures, but some people put entire smart contract, because you actually want to be transparent. What you're doing, you want other people to know and really look at that and really understand this is what is going on, rather than you try to keep your code hidden and expect people to believe you. So these are fairly old smart contract that was deployed somewhere in 2017. And you have a few things. I'll talk about some of these. So this is like a compiler directive saying I'm compiling this with the version 4.18 and few other things. But so there are some function definitions. I think we should be able to see the list of functions. Yeah. So, okay. So here, from this code, extracted set of function definitions are here. And if you remember, there was a function called withdraw, and that is this function. So it takes a unsigned integer 256-bit value as the input value. And there are a few additional things which you can really ignore at this point. So once you compile this code that we see here, you get this binary code that we are seeing here. So essentially, if you take the original one, compile with the same compiler version, you should essentially get this. Sometimes you can decode back and try to get the source code to a certain extent, but may not necessarily work all the time. Okay, so maybe I'll stop for a second. And if there are any questions, happy to answer. If you want, just unmute your mic and ask, or if not, just post it on the chat. I'll give about 30, maybe 15 seconds to see whether there's something appearing. If not, I'll move on. Any takers? Okay, as usual, I'll move on. Anyway, so now I ended up talking about quite a lot of things. Let me share my screen again. I ended up talking about quite a lot of things. So let's try to kind of understand what was really happening behind the scenes. I'll stop this one and I'll leave this one. Again, if anyone of you wants to use this, try this one. Only thing is it's gonna eat quite a lot of your CPU time and memory, mostly CPU. Okay, so there's actually a question. Is there a way to find two ways to minus? Okay, I'll actually come to that question a little bit later. Is there a way to find the miners in the network? Of course. So for an example, I just closed that one, but that's fine. Maybe I'll just go back to this one. So like here, how we are able to tell these different mining pools are based on those addresses. Is there a way, so if you're really asking like whether you can find the actual miner, it depends. So let's say if you have this hash string, but if you're really trying to find who is behind this hash string, it may or may not work. So for an example, so this is the address. And sometimes, okay, so these people are at least saying who we are. So this is called a mining pool called the flex pool. So if you go to our website, you would kind of find the details, but there can definitely be anonymous miners which don't mention the name. Now, whether you can really trace them or not depends on what other transactions that they may initiate. So for an example, when they build a block, you get Ether. And if you try to convert this Ether to, let's say, dollars or something like that, then you have to go through an exchange. And at that point, you could try to figure out where this request is coming from, which IP address, and you may be able to do that. Or exchanges may have certain conditions, like if you are going to be a customer of our exchange, you have to give your valid ID and things like that. So that's kind of the way to track this, but that is not necessarily successful all the time. I'm not sure whether I really answered the question fully, but of course we can kind of get a broad understanding around who is around, but not necessarily the individual behind a particular address like that. Okay, so there's another one. How to find the validators on certain network. Oh, well, I'm not really sure what is mean by a validator. At least in the Ethereum network, there is no validator. Or do you mean miner? So maybe I'll park it here at this point, but we can come back because I'm going to talk about a few of those, so probably kind of give you a more consistent terminology. as well. Okay, so if I quickly move on a little bit, so I understand there are mostly undergraduates here, and some of you may not necessarily have done, let's say, a class on security and things like that. So because of that, I'll quickly talk about essentially 3 or 4 slides on some of the technologies behind this. Otherwise, what I'm discussing may not make much sense. So you may have heard of a hash map and hash table and things like that. So essentially what happens in hashing is you have a particular function with a certain set of properties that if you give some input, it produces an output, but this output has some set of properties. So for an example, you can give a large volume of data from this side, but it produces a fairly small datum like 256-bit hash. So it can essentially map an arbitrary size data into a fixed size data. So what happens is if you have a larger file, you kind of go through this loop, and then somehow produce this output, which is fairly small. So this kind of act as the signature of this file. So this return value from this function is called the hash or the hash value, hash digest, or just hash code and things like that. So this one of the key properties around this function is if you change this input, your output typically substantially changes. So for an example, like if you look at this one, so fox versus the red fox, blah, 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 but this is definitely different. But if you look at the second one and the third one, so this is over, whereas instead of V, you have the U here. But if you look at the hash corresponding hash value, this is very different. Again, like these are represented as hexadecimal values. So this is one of the most important properties about hash. And there are a few other properties like given this hash value, you cannot go back and generate this input. And it's extremely rare, 2 different inputs would produce the same hash value as well. So there are a range of algorithms, but some of the more popular ones are like MD5, SHA, SHA3, like that. And you could also kind of decide how large this output that you want to be. So like 64 bits, 128 bits, like that. Now, again, if I go back and look at one of these transactions, or let's say a block or anything like that. Now, if you look at here, we have a block hash. Let's go down. This. So this is essentially 256-bit hash of all the content in this particular block. Number is this one, which actually does not have any transactions, but there are a few other attributes of that block as well. So if you put all of that as the input to this side, and if you get the output from this side, you get what we saw there. And then another term that you would typically come across when you talk about blockchains is this idea of a Merkel tree. So it's essentially a binary tree where you try to summarize the set of transactions and their hashes using a single hash. So what happens is, if you remember, there was a block with about 420 transactions. Now, while you have that 420 transactions, their corresponding details, including their hash, you could also generate a single hash out of that 427 by calculating this binary tree. So what you do is you take 2 transactions, take their hashes, and calculate a new hash. So what happens is into this function, what goes in as the input is hash of one transaction and a hash of another one. So you concatenate those two and generate this hash. Then you take this branch and generate this one. And then again, this and this to generate this one. So this root hash is essentially what goes into the block as the representation of all the transactions in the block. Why this is important is this is pretty small, because instead of, let's say, 420 transactions, we are going to transactions hashes, we are going to record only one hash here. And the other thing, the beauty of this tree is if any of these hashes changes, let's say someone fiddled with this transaction 4, because of that hash changes, that means it is going to change this one. That means that is going to change this one, which means it's going to change this one. So if someone fiddles with this, you can very quickly figure out this block is no longer valid because at least one hash is invalid. Because of that, this root hash is going to change. Then the other important thing around blockchain is this idea of public key cryptography, also what we call asymmetric key cryptography. Without going into much details, what really happens is you have two keys. So one key is supposed to be public, other key is private. So if, let's say, if you lock something with one key, you need the other key to open it. So depending on how you use these two keys and the order, you could either achieve encryption or what is called digital signature. Again, there are a set of algorithms to do this. Some of the popular ones are RSA and elliptical curve ECC. And again, you have this option of generating outputs with so keys with certain lengths. So like, let's say 128 bits, 250, and 160. In typically, like in bit Ethereum, you use a 160 bit key. Oh wait, key is still no, key is longer. It's just the address is shorter. Sorry, I'll explain what I mean by 160 later. So what really happens is when we have these two keys. One is the public key that anyone else is supposed to know, and the private key is the one that you hold on and you are supposed to really protect that. If you so think about this, like when you go to a bank and let's say you're trying to withdraw money, you take this withdrawal slip, you fill up the details and you sign that. So how you prove who you are to the bank is through your signature, essentially. So that is what the bank would validate. So like that, we have this digital signature in this space. Now, if someone is able to forge your signature, of course, they could appear like you. So that is why we need to protect this private key. If someone else knows this private key, you have a problem because they can essentially control the assets that you own. Now, okay, so let's say there is Alice and Bob who are engaged in this transaction. Alice wants to transfer 5 Bitcoin to Bob. So what Alice would do is Alice would form a transaction saying, I'm so-and-so, this is Alice's address, essentially so-and-so means Alice's address. And the receiver's address is the Bob's address. And I want to transfer 5 Bitcoin and put few other attributes that are related to your transaction. And then you sign that transaction. So in order to sign this transaction, because you are going to send your money, so you should be the only one that should be able to do this. So you sign your transaction with your private key because that is the one that you hold. And then how does the Bitcoin network knows that this request was transaction was actually made by Alice? Is the network knows your public key. So this from these two key pairs. So by applying your public key into your transaction, they can verify, oh, this transaction was indeed signed by Alice, not someone else. So in that case, that is a valid transaction. Of course, you need to make sure the transaction is well formed. Let's say all the other attributes need to be correct as well. If so, the network would accept this request. And once this transaction get included in a block, Bob will have 5 Bitcoin and you will lose 5 Bitcoin. So now in this case, in the blockchain networks, we don't talk about Alice or Bob and things like that. We talk about their addresses, which are essentially long binary strings. So for example, it could be something like this. Now, so based on the previous question, even some all the time. So actually, most of the time we don't know, but in few cases, let's say we know. Okay, so if we talk about Bitcoin, now again, like I went through Ethereum, but if any explorers, but I'll go to one side that you kind of get access to about 15, 16 blockchain. So this blockchain is one such website. Like if you look at this one, they list data from quite a lot of networks. And if I just go to Bitcoin, and let's try to get a more recent block. So the most recent block is block 740,311. Let's click on this. And this is the block hash. This is essentially the hash, things like the hash I was talking about. This one was mined today, few minutes ago, probably. And this thing had 2,879 transactions. And number of inputs to that transactions, the number of outputs, we'll talk about them as we go on. And this is essentially who built this block. And what else I want to talk about? Okay, so total input in terms of Bitcoin, this particular transaction included 17,797 Bitcoins, about half what? Oh, that's quite a lot. $519 million. And about $3,400 was just paid in as the transaction fee. So whoever the miner that built this block is going to get quite a lot. But on the other hand, you need to understand it's extremely computationally expensive to build this block. So miner may have even sometimes spend more than this much money to actually build this block. Okay, so if you go into technical details, this block is about 1.5 megabytes. And so this is the Merkel root I was talking about. So all these 2,879 transactions are essentially captured as a signature using this Merkel root. And there's something called the nonce we'll talk about soon. And a few other things like weight, difficulty, bits. And then this is the list of transactions. These that is included in this particular block. But if you click this, it will open up more and more. Let's see who actually sends so much money. Let's look at the transaction with most amount of money, maybe. Yep. So this one, $280,000. Not a lot. Yeah, that looks like the biggest one. Okay. Oh yeah. No, wait. Oh no, sorry, 280,000. It is $280 million. So just jump into this one. Somebody did this transaction, and this is the sender, and that sender send this into two transactions. One is essentially a payment, this is a fee, and this was a transaction, essentially money going from this address into this address, plus a fee going into the miner. Just to see what this could be, in case if you know the details. Nope, we don't really have much details about this particular address. But if you really look at this one in terms of money this particular address received in the total history, what are we talking about here? Trillions, $48 trillion. Okay, so anyway, so let's go back and continue from this. Okay. So what we are really doing is we are building a block by including a set of transactions, then we move on to the next block like that. So Bitcoin was proposed in 2009, 8 actually. There is a typo here. This is 2008. And a little bit later, a couple of months later, this implementation came out. And today this has become one of the largest networks where a block gets generated every 10 minutes or so. So if I very quickly go through another example, let's say someone is trying to send 2 Bitcoin, BTC means Bitcoin, like USD means dollars, to Bob, they would, so let's say it's Alice. So Alice would form this transaction, create a transaction, and digitally signs that. So to do that, Alice would need her private key. And so you send this to the network, and the miners will receive this transaction. They would validate whether this is really coming from Alice by knowing Alice's public key. Publicly is supposed to be known by others. And you could even attach this public key when you send the transaction. It depends on how you implement the network. And that's in most cases you actually attach that, not that the network really remembers your public key. And then if this is valid transaction, the miner try to put this into a block and try to build this block. So if you are successful, you can build this next block and add that block to the rest of the network, and you broadcast that to everyone around the world that is running part of this network. And if they also agree your block key is valid, what I mean by valid block key is you have included transactions that are valid, and you have built the block in the way that it should have been built, and then that becomes a valid block. So probably this would answer that question to a certain extent, like who are the nodes in this network. So let me open up this site. This is again a site that shows like live nodes in the Bitcoin network. So as of now, not necessarily extremely accurate, but at least this website is aware of 16,000 Bitcoin nodes. And in most cases, you don't necessarily know where they are even from. Quite likely to be part of this could be China. So about more than 50% of the nodes, you don't necessarily know the location. But there's still like a significant number running in countries like US, Germany, France. Europe is still very active in this space, and even places like Singapore. So these are essentially where miners are. Again, if you go into the site, you could actually do a little bit more deeper analysis. So again, different agents, like these are essentially a set of nodes or group of nodes, and from which countries, which network. These are essentially like ISP level networks. So quite a lot of people run their Bitcoin nodes on AWS, and some of them remains anonymous under a VPN. So Google Cloud even is here, like that. You could explore few additional details as well. But and we could definitely find the IP address of a miner, but we don't necessarily know whether that IP address is behind a VPN or not, or maybe behind a net and things like that. Okay, so what happens here is essentially you have an account. Now this is in Bitcoin world, this account is a little bit different from your bank account. So it's more like this. So think about your wallet. So you have coins and notes in your wallet. And so let's say if you have a 100 rupee note, that is like you own that much. And if you lose that, you lose it. So you kind of take that idea and digitalize that. So you have an account. So your wallet is like your account actually. So it's not just a single note. So let's say you have actually 512 rupees. A couple of 100 rupee notes, and let's say 12 rupees in coins. So like that. So how you identify your wallet is based on these two keys. One is your public key, which is used to create your address. So your wallet will have a unique address, and that address is generated based on your public key. And your private key is supposed to be private. It is to be used only when you're making a payment or something like that. Let's say when you're doing a transaction. Now, the state of the blockchain is the account balances of individual users. So you have a wallet, your friend has a wallet, let's say a friend's friend has a wallet, like that. So let's say if there are 5 billion people using this network, or let's say 5 billion active addresses or something like that, each one's collection is essentially the entire network state. So as we said, transactions are grouped into blocks. Blocks forms the blockchain. Now, if we talk about this little bit more detail, now, so let's say this example of, let's say you have a 100 rupee note and you're trying to buy something. Let's say that thing worth only 40 rupees. But when you give this to, let's say, the merchant at the point of sales terminal or whatever, and let's say so think about even a credit card transaction or something like that. You go and scan your card, you pay that, and there could actually be a transaction fee included, or you may be directly paying that, or you may be indirectly paying that as well. Now, in this example, let's say you had 100 going in. So let's say this is like your 100 rupee note, and you're paying someone $40, 40 rupees for whatever the thing you're buying. and they gave you 50 rupees back, and you have to actually spend, let's say, 10 rupees as your transaction fee. So now you have 50 rupees in your wallet. Next time you can spend this 50 rupees in another transaction. So let's say you have 50 rupee note, and that can be spent in the next transaction. So a typical transaction can include one or more inputs and one or more outputs. So in this case, there are two outputs. One is the actual payment and the money that you get back. Or if you really want to, let's say, spend this 100 rupees and pay two people at the same time. So this is like paying one person, and this is like paying the other person. Now, each of those transactions need to carry this proof that I'm Alice and I'm signing this. So what you do is really you form this transaction saying this, let's say this is Bob, this is Charlie, who are going to receive your transaction, the money. And so you digitally signs this one. And then you kind of have this linked list of transactions. Let me just, okay. You can have this linked list of transactions where like you spend this money and whoever got your money, let's say this is Bob, Bob is going to spend that money as well. I'll share these slides, but but the key term here is this idea of UTXO. You may have even heard of this one. So this is called unspent transaction output. So unspent transaction output is essentially like this 100 rupee note that is in your wallet. You have not spent that. Now, if you spend that, you get this 50 rupees back. So that is your new UTXO, and this UTXO is no longer valid because it has been spent. Part of that came to you. Let's say part of that was paid to the merchant, and part of that also paid to the miner as the transaction fee. So Bitcoin does not. So like, let's say if you go and ask what is your current balance in Bitcoin, Bitcoin cannot directly give you that because they need to count all the UTXOs that you have. So this is like if someone asks, tell me how much money you have in your wallet, you have to actually go to the wallet and count them. Not that you maintain a balance. Whereas if you think about the bank and your, let's say the bank, how the bank maintains the balance, they have an account number and they have a balance. So that's a little bit different from at least how Bitcoin works. So Bitcoin uses what is called this UTXO model to say essentially these are like the notes or the coins that you have with you that are not spent at this point. Now, let's go and look at one of these addresses transactions in a little bit more detail. Let's take maybe this transaction. Okay. Now, if you look at a little bit of details here, this transaction was included in a certain block, and the size of the transaction is only 255 bytes, pretty small. And forget about most of these, they are not critical. But so this is essentially you're the sender, and this is your UTXO that you're going to spend. And this got split into three outputs. So this is one input, and this is three outputs. So there are three recipients. One is, let's say, this payment, which is still big. Here's another payment, and then there is another payment. Plus, you may have also paid a transaction fee as well. Of course, you can put a zero as a transaction fee. Your transaction may or may not get included, but in this case, only 0.81 cents were paid to send quite a lot of money. So this is actually not bad to send this much money. So to transfer like what $11 billion, only 81 cents was spent. This is not going to be the case all the time, but possible. And few other details like this transaction was included in a block about 14 minutes ago. And this is the hash. This is essentially the unique signature of your transaction. And so who is the sender, who is the receiver, like now. Now, if you take this transaction and also look at all the other transactions that are included in a block, so this is like the block format. So let's say this is transaction one, identified by its hash. Here's another one like that. We have, let's say, 8 transactions. Now, you summarize all of these n transactions. So let's say if you had n transactions here using this one hash, which is the root of the Merkel tree. And that is what we see here. And then there are a few additional things like the version, Bitcoin version that we are generating this, and the hash of the previous block. So this one, so it's, let's say, ending with D5. So we see D5 here. And the timestamp, this is a Unix timestamp when the block was generated. Not gonna be very accurate, but let's say if it is generated now, it won't have a timestamp that was yesterday or tomorrow. It can be invalid up to like I think about 2 hours. And then this is the size of the block, and then there's something called the nonce. And then whenever the next block get generated, it will be pointing into this block's hash. So what happens is, if you combine all of these as your data, and if you calculate the hash value, you should get this particular hash value. Okay, again going back, and now let's go back to this block. So one more back. Oh, the block summary. Anyway, okay, just click on this. Yeah. So this is the block 311, the one before, one after. And this is the hash of the block. So if you look at this one, this had this set of leading zeros, and it's not very different from this one. And then at what time this was generated, how many transactions. So this thing had 2000 plus transaction included in, and the number of inputs. So in some of these transactions, you had more than one input. So that is why you have actually this one. And if you look at the outputs again, for this many transactions, that means you had multiple outputs. So more than one in and more than one out. So this is just the value of this whole transaction. And whoever built this block gets a reward of 6.25 Bitcoin, that is 182,000 USD for generating this. What else is interesting? Okay. So again, the size of the block about 1.5 megabytes. And this is the version number. That in that slide was just an example. And here's the Merkel tree. So this is calculated using all the other transactions, these ones in this one, and the nonce, and few other things. We can skip them for the moment. Okay. So let's go back. Okay. Now, you may have heard this term called proof of work, or at least the word mining. So mining means essentially taking this set of transactions that are pending to be included in a block, building the block, and advertising that block to the rest of the network, saying, I'm able to build this block, and here are the details, and here's even my proof that I actually built this block the proper way. So all these miners, like we saw, like 16,000 nodes are in the Bitcoin network currently. Not necessarily everyone, but let's say at least 99%, I'm pretty sure, is trying to mine a block. So they compete to create this block by solving a puzzle, because otherwise anyone could put blocks transactions into a block and broadcast to the network saying, here's my block. So rather than all the 16,000 trying to do this, you give them a challenge. So whoever is able to solve this challenge is essentially a miner that is able to create a valid block. So this is what is called proof of work. And it's based on in Bitcoin, it's based on an algorithm called the hash cache. So the idea would be this. So you have this set of transactions. Given these, you can calculate the Merkel root and few additional things here, except this nonce. So on one side, you have this your data. So let's say all this data in this block, except this hash and this nonce. Everything else is given to you as your input to this right-hand side. And you're trying to find this n-bit nonce. like when you concatenate them together and apply to this hash function, you get a hash value as your block hash that has a certain property. So in this case, like in this example, it has a certain number of leading zeros. Now, given some inputs, calculating a hash is fairly straightforward thing to do. Of course, a little bit computationally expensive, but you can calculate. But trying to calculate a hash that has a certain property, let's say you have to find a hash with only at least 4 leading zeros. That is hard because you don't necessarily know what would be a good nonce, because if you remember, I said, like, given a hash, you cannot go back and figure out what was the input. So without knowing the input, you have to pretty much try the whole search space here, or at least half of that space in average, to figure out a hash that satisfies this particular property. So this is essentially what happens in proof of work. You have some data. To that data, you concatenate a random number, and then you apply this hash function and you get an output. And you check whether that output satisfies a certain condition. So generate some random number, concatenate with that data, hash the two, and look at whether you satisfy whatever the condition that you're looking at here. So again, if we go back, this changed, that's fine. And so here's the nonce, and here's the hash value. So if you look at, there is a certain number of leading zeros. Now, more zeros that you have here, it's difficult to calculate. Less zeros that you have here, you have a much easier chance of calculating that. So what you'd really do is, you can even adjust the complexity of this calculation by actually saying how many zeros you need to really find. So this is called proof of work. Now, on the other hand, when you give me this block with this hash and the nonce, I can very easily calculate, because I know the nonce, I know the data, and I can calculate this and check whether the hash that comes out of this hash function is same as the hash that you're claiming to be. So this is essentially what we call validating a block. So if the hash happen to be the same, then you know the block is valid. So if we talk a little bit about the technical side of this is what is called an embracingly parallel problem, because there are no shortcuts to find what is a good nonce. So let's say if the nonce is even like 8 bits, you have to try 256 combinations, at least half of them. Whereas if this nonce is like 128 bits, you have 2 to the power 128 combinations. So you need to put quite a lot of computing power to solve this. So you could try to use specialized GPUs, or let's say ASIC's hardware to run this. So this function has this special nice property that is extremely difficult to compute, but easy to validate. So if you are the miner, you have to put massive amount of computing power to find this. If so, you have built a valid block. Whereas anyone else trying to validate whether you really did that, it's easy. So think about something like, it's very similar to, like, let's say when you sit for an exam. Let's say you spend 2 or 3 hours answering your exam paper, but your examiner does not really need 2 hours to mark that. They may be able to do that much faster, or maybe even 15 minutes, depending on the type of questions and things like that. So generally, when you generate a new block, miner gets a reward. So that is actually what we saw here, this 6.25. So what happens is, whenever a block is generated, a new cycle starts. You look at the set of pending transactions, you grab some of them, build this block, which is pretty easy. But after that, you have to solve this puzzle. That is where actually you spend most of your time. Now, in Bitcoin, you generate a block every 10 minutes approximately, in average. So from that 10 minutes, actually you spend, let's say, 9 minutes, 59 cents actually solving this puzzle. Because building the block is pretty easy, but not solving the puzzle. Whereas in the Bitcoin, Ethereum network, these blocks are like every 13 to 15 seconds. So you build a block in milliseconds, but actually solve the puzzles for the rest of the time. So once you solve the puzzle, you propagate that to the rest of the network. Now, when you do this, sometimes there is this possibility that multiple miners may build valid blocks at the same time, because you are not asking for an exact hash, but you're asking for a hash with a certain number of leading zeros. So this can happen where you may have something like, for this block N, there could be two competing blocks. If you remember at the very beginning, we had a block when in that visualization, we had a red block. So those are essentially competing blocks. Now this is like you have two alternative versions of your state in this block, because the set of transactions in this block may not necessarily be set of transactions in this block. So you need a way to resolve the conflicts among these blocks. So that is where you have what is this called the Nakamoto Consensus. The Nakamoto is a pseudonym behind Bitcoin, where he or she said, okay, that's fine, but let's wait a while to see what other miners would do when they build the next block, or let's say the block after. Now, after a while, you would see one part of this network growing longer, whereas other part is not. So the longest chain wins is essentially what the Nakamoto said, or Nakamoto Consensus mean. There can be competing blocks for a while, but after a while, the peers will naturally realize quite a lot of blocks do not include this block as a parent block. Because of that, when this branch grow longer, you just ignore this one. So it is possible, like let's say, if you are trying to buy, let's say, a bicycle using Bitcoin, and if you are the seller, just because you got money, or let's say you got the Bitcoin in this particular block, you better not hit the bicycle. You better wait a little bit. So in Bitcoin, this is about, the waiting time is about 1 hour for, let's say, 6 blocks, approximately 10 minutes each. Then you have a pretty high, extremely high confidence that your block is no longer going to be not in the longest path. Whereas the moment you got the money, if you just send the bicycle, you may be at risk. If the transaction was here, after a while, you may be not in the longest path. Okay, so we already talked, I didn't explain the Ethereum detail, but I showed that visually. So Ethereum is pretty similar in the concept of when it comes to cryptocurrency, but the biggest thing that it brings into the picture is this idea of smart contracts, where you can actually run some piece of logic, let's say a code or a script on this blockchain network. And because of that, you can pretty much do anything that you can put into this piece of code. So it's not only about cryptocurrency, it is about who owns what. Let's say who owns art, or you may have heard of these NFTs, non-fungible tokens, which is a metaverse and things like that, which is a big thing today. So all of that is possible because of your ability to program this, not the network, but runs on that network. So Ethereum is called a second generation blockchain simply because Bitcoin is like first generation. They only focus on the cryptocurrencies, whereas Ethereum take this further into the next level. Now, it uses a similar structure, but the key difference is these blocks are generated much faster, every 15 seconds, let's say. And again, like there is a limit on the size of the block that you can generate. In Bitcoin world, it is defined in terms of megabytes, so 4 megabytes today. Whereas in Ethereum, it is defined based on something called gas. And if you like, let's say if your maximum gas size was 15 million, you could only include standard 714 transactions, but you can actually have much less than that depending on the type of transactions that you include. But if you remember, there was actually a block with 30 million. So this slide is slightly older because they have recently increased that number as well. Now, this idea of gas, could be a little bit confusing. Think of it like this way. So let's say if there's a car, that car runs at a certain efficiency. Or let's say it needs 8 liters to run 100 kilometers, or other way around. Let's say if you give 1 liter of petrol, let's say you can drive 12.5 kilometers in average, something like that. But then to buy that liter, you would pay a certain price, and that price always vary. So that is what is called the gas price. So when you execute a transaction, you have to pay something to the miner, and how much you need to pay to that miner in Bitcoin is entirely voluntary. So you could decide how much you want to pay. If you're paying a lot, miners would likely to include your transaction because they get a good cut out of it. Whereas if you're going not to pay, or if you're going to pay very little, your transaction could take a while to get included in a block because miners are not very interested in your transaction. Now in Ethereum world, this gas limit, you cannot decide. This comes from the network. It depends on the complexity of the operations that you're carrying out in your smart contract. So let's say if you're just doing transferring Ether without executing any smart contract, there is a default gas limit. So no matter what you do, you have to pay 21,000 gas, otherwise your transaction is not considered. Whereas when you execute smart contracts, of course, you execute more complex instructions. So this is like CPU level instructions. So depending on the CPU level instruction that you execute, you have to pay a certain fee. So that you define as what is called the gas limit. So what you do is when you send the transaction, you would say, I'm willing to spend this much, but for some reason, if your transaction actually needs more than that, your transaction will fail. This is just in a way, this is more like a way of protecting yourself. Let's say if you accidentally wrote an infinite loop, you don't want to pay, let's say, $1 million as your transaction fee. So that also kind of gives you a safety net where you could limit how much you are willing to spend on this one, even if you have a bug in your code. And the price is essentially determined by the market. So when the network is very heavy, or let's say heavily congested, price goes up. When the network is not so heavy, price goes down. So this is Bitcoin. Let's go to one of these Ethereum ones. Do I have a transaction open? Nope. I think I had one here. Yeah, too much. Okay, so in this one, if you look at the gas price is this much, and the gas limit, you set it to this one. So when you send the transaction, you said, I'm willing to spend maximum of 36,027. How you estimate? There are various ways of doing it. Let's not go in there. Go and discuss about that at the moment. But actually, your actual expense was only 30,000 something. Now you need to multiply this 30,000 by this value to get your actual transaction fee. So it is like you are going to go some sort of a journey, and to go to that journey, you have to spend, let's say, 30 liters of fuel. Whereas when you start the journey, use it. If it is going to make more than 36 liters, sorry, I will stop at the middle. If I may stop, that's fine. But I'm only willing to put only 36 liters into this vehicle. Let's say that was your capacity. But actually, when you end the journey, you only spend 30 liters. But for each liter, you spend this much Ether. Now, if you convert this into dollars, you can also see that. But if you really look at this value multiplied by this, is actually this. So it's not a lot. It's only $1.26. Now, in the Ethereum world, we estimate these using something called GUI, which is essentially like 1 to the power minus 18 Ether. So it's a pretty small value. So that is why you have a very small number here. But at the end of the day, you were spending fairly little amount of Ether. And then Ethereum transactions are now very different from Bitcoin ones. You have like a sender, so that is a format address is a sender, receiver. You can have a value. You have these additional things like the gas limit and the gas used and the price you are willing to pay. So this is like your full tank capacity, and this was actually what was used, and this is how much pay for a liter and things like that. So this is a timestamp when in which block this was included. This is your transaction hash. And if you look at a typical life cycle of a smart contract or a transaction, you submit a transaction that goes and wait in a pool. And after a while, if you're paying with little transaction fee, miners may not be interested, or for whatever reason, miner may decide to drop it. If they don't drop it, they would eventually include that in a block. Now, if you get included in that block, and if your block is in the longest chain, your transaction becomes committed. But unfortunately, if it is in a competing block, your transaction will get lost because it's no longer in the longest one, and you go back to the pool and wait to be included. Again, while waiting, you may be included in a block, you may drop. And you could, of course, replace a transaction by sending another transaction, not guaranteed to work, but sometimes can work. Say, for an example, you send a transaction, you realize there is a mistake, I want to correct this, it's still not in a block. So you could try to send another transaction, particularly with a higher transaction fee, and hope that miners, because miners usually are greedy, they're looking for higher transaction fees, they may include your new transaction and discard the previous one. So essentially, not really canceling out in the sense it does not execute, because the new one is the one that is going to get executed. Now, I don't want to talk about the block format, but because Ethereum also has the smart contracts, they maintain their own state. So essentially, like a program has its own variables, like either the variables that are in the memory or the persistent variables. Because of that, there are quite a lot of things that are happening here that you need to maintain. But one of the most important things probably to remember about Ethereum, maybe I actually missed this one. Okay. Now, Ethereum does not use UTXO. Instead of that, it uses what is called the account balance model. So this is essentially like the bank's model, where a bank knows your account number and you have a balance against that account number. So it's not like the number of nodes or coins in your wallet. And then a very quick introduction to smart contracts. Smart contracts are essentially programs that you can run on the blockchain network. Now, the thing is, because the network is immutable, your code is also immutable. So once you deploy a code, no one can really modify that unless, of course, you build certain ways to, let's say, replace that particular version with a new version. Actually, not really replace. It's just you tell the users don't use the other one. By putting something like a proxy, you could redirect them to the newest version of the smart contract. So you trigger this execution using a transaction. And in terms of programming, this is very similar to, let's say, something like a Java program. You have the smart contract code, which is like a class. When you execute that, your instance is an object. So when it is running in the blockchain, the deployed contract is similar to an object. So code is deterministic because it is immutably stored. Everyone would agree this is exactly what will happen. If you remember, I showed you the Uniswap contract. Since 2017, it is there. It is being heavily used by people, and they understand what is going on, or at least they think they understand the code by looking at the code. So why smart contracts execution is trustworthy? Because Bitcoin solves this double spending problem. So like that, once you deploy a smart contract as a transaction, it is immutable. And given a certain input, you know exactly what would be the corresponding output. So you execute these transactions to get different things done. So there is a transaction creator who would deploy the smart contract, and then someone can execute the smart contracts. And there can be two types of transactions. One is point-to-point transaction. This is essentially you transfer cryptocurrency back and forth, and then you could invoke various functions in this smart contract. I'll just maybe I'll show you something. Okay. Hope you can see my screen. Don't worry about trying to understand this one. I could actually share a live sheet related to this. Essentially, with step-by-step instructions, you can write this program, a smart contract, and deploy this. Let me get my code. Okay. So this is a simple contract. Let's say some of you are deciding where you want to have lunch. And for that, you are going through a voting process. So the name of the contract is like essentially our class name is the lunch venue. And this is a processor, preprocessor directive, or essentially saying, I'm going to compile this program. This is written in a language called Solidity under version 0.80. And then when it comes to deciding where you are going to have lunch, you decide who is going to vote and what are the places you are going to vote for. Let's say Pereira's Cafe or something like that. So you put some venues and you maintain these hash tables. These are essentially hash tables on list of venues and list of friends. And you have few additional variables to count the number of votes and things like that. So there is someone called a contract manager. So not everyone can add friends who can vote on this. Not everyone can add a venue. So only this special role can add them. But if your name is there, you can vote once you start voting. So there is a function to add venues. There's a function to add friends. And then this is the function that is most important to everyone. They would go and vote for this. And once, so let's say we have a simple majority, not a very optimized code, but let's say as soon as you at least half of your friends, more than half of your friends vote, you would decide on a venue. And then this is just used to calculate the final result to figure out where you want to have lunch. Now, for example, so let's say I can compile this. So I just compile, just a tick saying no bugs in this code, and I can actually try to deploy this. I'm not going to deploy this to the actual Ethereum network, but there are 2 or 3 live test networks that we could use. Those are global networks. So I'm going to put this to a network called the Ropsten. And for this, don't worry about the details. I will just need to set a gas limit. I have put a pretty high value. Just because I don't want this to fail at this point, and I can decide on a value, but when we try to deploy, I can decide on the value. Wait, I need to log in. Don't worry, I don't have real ether. No. Okay, so I need to put an amount. Very likely in 15 seconds. Okay, don't worry about the details. So I created this one and I can actually see this transaction. My transaction is pending. And if I'm lucky, it could get included. So I'm not sending any ether. And if you look at the details, so let's say I set a certain limit and this is what I'm going to pay in terms of gas fee. Okay, it got included in this particular block number. So this number is different from the real network. This is the test network. So if you see here, there's a different network. Main is a real network. Oh, okay. So now I have a smart contract that is deployed as part of this transaction. And this is my address. So I can actually show this. So this is what is called a wallet, a Metamask wallet. It's like a digital wallet. And I have an address. Don't worry, this is not real either. This is the test networks either. So this doesn't mean anything. And so what I really did was, so if you look at, this is my address ending with 8F25. So 8F25 is what we really have. So this is something that I deployed. Okay, if anyone wants to play with this one, I will paste this to the chat. There's a chat. And then you could see this contract and you could even interact with this one. Only thing is you need to know my function definitions to interact with this. So this was actually the bytecode that I deployed. Because I did not deploy any code, you can't really see the original code. You can only see the bytecode. And this is my smart contract address. Now, how do I interact with this one? I can actually interact with this. So this is my deployed contract. So it has a set of functions. So I can add friends, I can add a venue, I can do vote, and I can get the list of addresses because some of these are public variables. So let's say like list of venues, list of friends, and these are, and some of public. So sorry, this is the venue and the friends, and these are the number of those. So automatically the compiler will also write the getter function for the public variable. So let's say I'll add a friend, and to do I'll not add a friend because I need the two things. To add a friend, I need both the friend's Ethereum address and a name. But just to show an example, let's say something like this. I will add a venue and I need to sign this transaction again. And I'm going to sign this. So you don't see this behind the scene. Actually, I'm using my private key. So if you really look at this one, this is my address. And this is generated based on my public key. If I get a little bit of desource, this is my public address, but my private key is hidden behind this. So they're actually signing this and sending this. So if I look at this transaction, I can actually go and refresh this. If that got included, I can see that. Yep. So I was able to add a new venue using a new transaction, and there are a few additional details here, but the more important thing is essentially this is what I sent. I call this function with a certain input, and if I decode that, it should tell me Uncle Sam. Okay, let me go back and also show you. Now, if I'm trying to look at the number of venues, I can just do a getter function call, and it should return me with the number of venues, which is now 1 because I added 1 place. So like that. So this is a browser web-based ID called the Remix. Okay, I will stop at this point. Of course, I was supposed to talk about Hyperledger Fabric, but I will stop at this point because I think we're almost there, and happy to answer a couple of questions.
Sir, there were some few questions on the chat, sir.
Wait, let me check. Okay, so there is a question saying why a lot of resource needed to build a block with few MBs. Okay, good question. We only have like 1.5 megabytes if you're talking about Bitcoin, and if it is Ethereum, few hundred kilobytes. It's actually not about the size of the problem in terms of data. It's about the difficulty of building this. Now, if you make it is okay, let me go to that slide. It would still be good to share that slide and talk about it. Perhaps it wasn't very clear what problem we are really trying to solve. Now, think of this way. Now, if anyone can build a block, we have a situation that everyone would say this is a valid transaction, that is a valid transaction, and that is not going to help us because we want to have a certain perfect history of records or record keeping. So that is where we want this longest chain. Now, if everyone start doing this, you would kind of go vertically rather than really horizontally trying to build this longest block where everyone wastes time. So what we're really doing is, it's not that this problem is hard. It's just you make the problem hard so that you don't want anyone to build this block. So it's in a way saying you are giving them a hard challenge, saying whoever is able to solve this problem faster now has the right to build a block. So hopefully only one would get this correct within this, let's say 10 minutes. Maybe 2, maybe 3, but definitely you're not going to have a situation there will be 100 competing blocks for the same block number. So same, when I say block number, like a position like this. So essentially what you're trying to do is you're trying to make sure we want to generate this and we want to make this hard for anyone to do that. So that is one part of the problem. Other part of the problem is if it is easy for someone to generate this, they could of course change the history. So let's say if you want to double spend. So Alice was sending $5 to Bob, for 5 Bitcoin to Bob. After a while, let's say Alice still wants to spend that 5 Bitcoin to do something else. Now UTXO model, that transaction has already been spent because you already used that. But how you can try to defeat the system is to kind of disregard that previous transaction. So let's say if it was included in a block like this one, you change that block. You take the transaction out of it. Now that means you're going to change. Oh, let's see. Okay, so let's say if you decide to, this was Alice's transaction to Bob. Alice wants to double spend the same money. So now means Alice can remove this transaction from the block and try to rebuild. Of course, to rebuild, you need to find a good matching nulls that satisfy a condition like this. Now, in order to do that, Alice need to now put quite a lot of effort to build this block. Not only that, because this transaction may have happened in the past, let's say even 15 minutes ago, someone has already built another block on top of that. Now, if Alice is trying to recreate the history, she has to not only fix this block, calculate that, and immediately go and do the next block. And after that, even do the one after. So while you try to defeat the network, other peers are also competing to build this. So this becomes a computation infeasible problem for Alice because the challenge is not just to get one block built, but build few more blocks compared to anyone else so that you have a new version of this state in the network, or let's say new reality in the network that is different from anyone else. I hope I answered that question. So it is essentially, to summarize, it is not about actually you really need to do this. You're trying to make this problem harder so that not anyone can build it. Even if someone build it, they cannot continue to build few more blocks very fast. So that is essentially how you really add trust into this whole network. Okay, so what are the other questions? Is Ether proof of work or proof of stake? Ethereum version 1 is proof of work. Version 2 is currently being tested or slightly deployed, I would even say, which is going to be version 2 soon. And that is what is called POS or proof of stake. So in that one, you're not going to actually spend quite a lot of computing power solving this. Instead of that, you would put your money to get your power to let's say power to build a block. So it's not a very simple idea, but if you translate this, let's say if two people are trying to build a block, one that has put more money into the system, let's say stake in the sense you have to keep that money aside, who has put more money has more voting power, or let's say more power to, or let's say more chance, probabilistically higher chance of building a block. Next question, can there be more than one nonce that can produce the same number of leading zeros? Yes, exactly. So that is why you have this multiple competing blocks. Because you're not looking for an exact hash. You're looking for a hash with a certain set of, let's say, prefixes. So in that case, it's quite possible two different nonces would produce hashes that look similar, at least up to the leading zeros that you want. What's the difference between proof of work and proof of stake? I almost explained. So here the proof of work is you solve this puzzle. Whoever able to solve the puzzle first is the winner. So how you can become a winner most of the time is if you actually have quite a lot of computing power, you can try to solve this puzzle because this puzzle is parallel. So let's say if it is a 8-bit nonce, you have 220, sorry, worst case 256 combinations to try. Now, if you actually have 200 access to 256, let's say CPUs, or let's say GPUs even, you can do this in a single instance because you have that much computing elements. So whereas if it's like 128 bits, of course, you don't have that many computers. But someone with, let's say, access to 10,000 CPU cores has a better chance of building a block compared to someone with access to only 10 CPU cores. So like that, in proof of stake, you put money or you lock money in the network. So let's say you put 10,000 Ether into the network and lock that to become a miner. Someone else put only 10 Ether to become a miner. So there are a few additional things happening here, but let's simply think this in terms of probability. So one who put 10,000 Ether has a higher probability of building a block compared to one who put only 10 Ether. So your return on investment is actually sort of proportionate to the money that you set aside. But there are a few additional algorithms running here, not just because you put that money. It is probabilistically distributed around others to make sure who is going to build the next block is not obvious. Any other questions? Yeah, something up here. What is proof of history? Not sure what it really means. There are so many proof of X, but if you're just talking about proving that how historical transaction has taken place, is essentially going back to that chain of blocks and showing that each of those blocks are correct. So how you prove that is easy. You have a nonce, you have the rest of the block, concatenate them together, apply the hash function. If the resulting hash value is same as the hash value in the block header, that's a valid block. So now you move on to the next block, verify that because that always links to the previous block. Verify that, move on to the next one. Anything else?
Hi, can you hear me?
Yep, sure. Yes, Rajat.
I have a question like how we can log into like this kind of a distributed network without having a central portal or something. We need some central place, right? Isn't it?
No, what you really need to do is to run. Okay. Now I showed you Etherscan, what I call a browser, a transaction browser. Etherscan or blockchain and things like that. So those are mostly to see what is happening in the network, not directly to transact. So you have to somehow connect to one of these nodes that are running in this network. Let's say I showed you like 16,000 nodes. So you somehow need to connect to one of these nodes, or you can run your own node. So for an example, like in Ether we were live, how we get that data that we see in that visualization is we run a node. So through that node, if I'm actually issuing transactions, I can do that. Now, the other thing is, say, there are APIs that you can use at free to a certain extent. If you are using sending more transaction, you can actually spend money as well. Let me again share my screen. Hope you can see. And I use this one. So this is what is called Metamask, a wallet. This allows me to interact with the network. So I'm using this plugin, And behind this plugin, when I send a transaction, it actually talks to one of the nodes that MetaMask runs. So you would need access either directly by installing your own node and connecting that node to the rest of the network, or you need someone else's node either through an API or let's say something like what we see here. Did I answer the question?
Yes, sir. Yes. Thank you. Thank you.
I'll share this smart contract example, which kind of gives step-by-step instruction on how to write the code and deploy it and all of that. You can try. Yeah. Does IPFS act as a private storage, the smart contract? Yes and no, in the sense it is a storage, but that is a storage that is actually not in the blockchain itself. So there's this idea of what I call decentralized applications. So like mobile apps, there are decentralized apps, DApps, in the blockchain world. Now, part of, like, even if you look at your mobile app, part of your data stays in your mobile phone, other part stays in cloud somewhere. So it's like that. So IPFS is more like what is stored on your mobile, like it is stored outside the blockchain. And then within the blockchain, so like in this example, when I say Uncle Sam or something like that, that is something that exists in the Ethereum test network. It's in the blockchain. So IPFS allows you to kind of put this bulk data outside the blockchain and somehow link them to the blockchain. So it's still a distributed file sharing let's say file storage system, but the data are not quite on the blockchain itself. It is outside. Is crypto legal in Sri Lanka? That's a good question. I heard few things and I'm not the person to answer. I think it is allowed to a certain extent, but it is more like if something goes wrong, you take your own risk. It is the case in most countries, but I would definitely say it is not as open as in other countries. Say, for an example, in Australia, you could buy, you can sell. As far as you keep paying taxes for whatever buys and sells that you do, you can do it. Only thing is, whenever you sign up with an exchange, you need to give your ID like passport or driving license and things like that. So one thing to probably understand is blockchain came up because of crypto, but blockchain is a lot more than crypto. Anything else? Okay, in the scenario of two competing blocks, how would a miner decide which block to consider as the previous block? Okay, good question. It's entirely up to the miner. Now, I can try to go to Etherscan, but I can't guarantee we will see Etherweaver and see with, oh, okay, we are lucky. There is a there's a red block. Let me share screen again. Hope you can see my screen. Okay, now this one is interesting. There are two red blocks. Now, if you're 348, it is, oh no, not 348 because they're the competing ones. Actually, this is interesting. Three 348s. In Ethereum, this can happen compared to Bitcoin because this happens much faster, only 50 seconds, whereas Bitcoin, we are talking about minutes. Now, this 349 has a choice of deciding any of these three. It may have a particular reason. Maybe it knows it is part of the F2 pool, probably because it wants their own blocks to be included because they get the reward as a collective, as a group. So it may have a preference to do that. Or it can just randomly design, or from which of these three that it wants to consider as part of being the longest. If you still look at this one, this still recognizes this block, but it did not recognize this one. Whereas 350 recognized this one. So there's a little bit of complicated things happening in the Ethereum to still recognize some of these blocks. But in this example, it was recognized not the subsequent block after. Next question. Is there any network that we can de-app freely without paying transaction fees? Unfortunately, only to the test network. So like the one I just deployed, you can use the test network to deploy, and you can even get free Ether to test things. But if you're talking about a production network, typically you need to pay, but there is no hard and fast rule saying your minimum transaction fee need to be this one. So even if you put 0, and if you are willing to wait days, hours, sometimes weeks, it may still get included in a block eventually. Unless it get dropped by all the miners in the network. But when I say all, we don't necessarily see the whole network. So as far as, let's say, one of that 16,000, keep that, and whatever the block that it generates, if it was lucky, of course, you can deploy without paying anything. But it's hard and it's not guaranteed. But if you want to do testing, use a test network. It's not very different from production network, at least in terms of functionality. And all the API calls, everything the same. In a mining pool, is there a computation divided into smaller parts and divided between? Yes, exactly. So nonce, let's say you have 256 possibilities if you have 8-bit nonce. So if you have, let's say, 16 miners in a collective, what is called a mining pool, you can split that 215 into 16 into 16 and say, okay, first node work on 0 to 15 as the nonce, next one 16 to 31, and 32 to 47, like that. Yeah, of course you can split, and that's exactly what is happening. So in the pool, depending on the computing power, so just think of this whole search space as a line, and you chunk it and give it to different nodes, saying you solve part of this problem, you solve part of this problem, and the miner who solves usually gets something. And even others, if you stay in the network for a long time, if you made a decent contribution, you will get something eventually. So the problem has become too complex. And essentially, let's say Ethereum, a Bitcoin network consumes same amount of like what Las Vegas consumes in a day. So it's not practical for someone to acquire so much computer resources and even keep paying their electricity bills. So it being the proof of work being a what is called an embracingly parallel problem, you can easily slice it and give it to different nodes, saying you solve this. Any more questions? Okay, maybe we can call it a day then.
Yes, sir. So I hope all the doubts have been resolved. So thank you so much, sir, for sharing your knowledge with us. And I'm pretty sure that everyone got a great understanding on how blockchain works. And I want to especially thank Dr. Sulochana for helping us with organizing this webinar. And thank all of you for joining with us. And again, sir, thank you so much. So I think we can conclude the session now. Thank you.
Sure. Just to add, I don't expect you to understand everything. And even if you don't understand, don't get discouraged. This is not an easy topic. And there are quite a lot of technical things happening. So just take it one thing at a time. Yeah. Thank you. Thanks for the opportunity too.
Yeah, thanks.
Bye.
Bye, sir.